Okay, so today we will continue with electromagnetic induction, probably finish this part. But I want to tell you that the classes that we join is sort of like counted by the number of hours that we have. So we can also consider today's class as a replacement for the previous class that we started late. So then we don't count today. Does that make sense? And then if it's needed later closer to your actual exam, then we will add on some classes if it's needed.
Okay.
Okay. So far, just to catch Jeremy up for what we've been doing, we have been looking at induction, which is basically the generation of current whenever you have a conductor or a wire cutting the field. Okay, so I think maybe today my computer can run some simulations. Since it's recorded, give me a sec. So normally when it comes to Faraday's law, right, the best way to learn this is generally tied to the idea of actually being able to see it in person. Also at the same time, I find that most of the time it requires us to buy a lot of lab equipment. Simulation would be a good stand-in. So generally speaking, as it loads, we have a conductor and then we also have a magnet. You see the magnet, all these field lines that we're drawing, as long as the magnet is moving, so all the conductor is moving. Okay, so for example, in this case, the wire is moved downwards. Okay, so this means that the magnetic field lines are cut. Okay, so when the magnetic field lines are cut, the milliammeter will show a reading. This means current is induced in the wire, there is induced EMF across the wire. So there's also an energy conversion. When you're moving the wire, you are converting kinetic to electric. Okay, and at the same time, here is another one. Let's say I have see what can I do? This one. Yes. Okay, so for example, these little tiny arrows are your magnetic field lines, okay? And right now there is no current because the light bulb is not turned on. If not, I can replace it with a voltmeter. This one is not turned on. But if I move it, you will realize that as I move the magnet bar into the coil, it will deflect to the negative side. When I move it out of the coil, it will deflect to the positive side. So when that's moving, right, you see all these lines. These lines are cutting the coil. So this means the coil electron is actually moving. Okay. If let's say I leave the magnet inside like that, the electron will move also. So I put the light bulb here, there's nothing. Okay. It will only turn on or there will only be current if I move it out or if I move it in. Move it out, move it in. Okay. Of course, when it comes to the light bulb, you cannot tell the direction. So in other words, right, I need the field lines, if you observe these lines here, to actually be cut by the conductor. Okay, there are many ways, like if I don't want to move magnet, I can also move the conductor, it's just a matter of who is moving this. So in this case, there are many examples that we've done, okay? And also at the same time, there are certain factors that will affect the size of the induced EMF or the induced current, or in this case, the brightness of the bulb. You realize that if I, let's say, increase the magnet bar strength to 100%, this is so much more brighter. So I can make the magnet stronger. Okay? Or I could, let's say I go back to 75. Okay, and instead of making the magnet stronger, I can move the magnet bar faster. So when I move it faster, you can see the current or light bulb should be brighter. Okay, of course, this kind of thing is better to use this one as a magnitude. Another way to increase the current or the current induced is to just increase the number of loops. So when the number of loops is more, here got 3 loops. Okay, you can see that the current is very large when the magnet bar passes through. So here is a list of the effect that will change the size of the current inside the coil. Number one, you can move the magnet faster so that there is more lines cutting through the wire. Number two, you can increase the number of wires or number of turns. Number three, you can use a magnet bar that is stronger. Or number four, you can use a larger. Example, this one, I can make the coil larger. Okay, so let's say I make the coil larger. Okay, I go back to 2. You can even see that this is so much more brighter just by making the coil larger. The reason why you cannot always see it is because of the lag. Computer is running, but you get the idea. Okay. So number one, if you cut the field lines, there is current. Number two, if you cut the field lines more, there is larger current. Okay. So those are the two main ideas that we have here. I've listed down already. If there is a change in magnetic field, EMF is induced. The greater the rate of change, that means there is more change in a given time, greater the EMF. EMF is basically like the voltage of the battery. Okay, so this is the first thing that we learn. When do we have this current and when don't we have this current? The second thing that we learn is actually the direction of this induced current. Okay, so direction of the induced EMF is always opposing the change producing it. So it's 反对党, they oppose you. So let's say, for example, when we move the magnet bar in, let's say I put back the meter here. When I move the magnet bar in, it goes to the negative side. When I move it away, it goes to the positive side. Okay, so let's say, for example, if I want to know whether the direction of the current is positive or negative, I got two methods. Number one, I think about opposition. For example, when the magnet bar wants to go towards the coil, this coil will be like, make this side not pole so that the magnet bar will not go in that easily. This is to oppose the approaching magnet. Just like if the magnet want to go away, this one will become south pole. Because the magnet is leaving, so you want to attract back. This is Lenz's law. Okay, another way that is slightly faster is to use your Fleming's right hand rule. Okay, so we learn to use our Fleming's right hand using obviously our right hand. The first 3 fingers of your right hand will show different things. Okay, so the thumb shows the direction of the force, the index finger shows the direction of field, and the middle finger shows the direction of the current. This force is basically direction of motion. So for example, if we look at this picture, and if you want to, you can take out your right hand just to check. The direction of F is pulling the wire to the left. So because the magnetic field is pointing upwards, there are many field lines pointing upwards, so the current will be pointing here. Okay, so yes, this is basically what we've done so far. We practice the properties and we discuss how do we find the direction of the current in straight conductors. Right, so today we're going to do more examples, mainly involving length. Other similar examples. I don't know what page this is. Right, this is page 4. So, pro tip, if you want to practice your IG with all your things that you need to do for SPM, is to go to this website first, paper.sc. It's free. And you key in the code for your syllabus, 0625. You might be thinking, teacher, how I know my syllabus is 0625? Then notes here, I got 0625. Okay? You key in your syllabus code. If not, then you just search physics lah. Don't choose the A-level one. Okay, physics. So this one, they have answer until 2019. The reason why there's no 2020 and after that is because the student who did this website graduated already, so he went and do other things. So if you want the more recent ones, answer or you want to practice certain question, you can go to Google Drive for that. But what I like about this one is if you click in the year, you are sitting for paper 2, paper 4, and paper 6, right? So for example, if you want to look at paper 4, you click into paper 4, they can display the whole question for you, but I like to look at this one. So you can see there are 9 questions, and each question, for example, let's say I want to do a question about, I don't know, circuit. So I can click question paper. This is the question paper. Okay. Then I can also look at the question paper, click on this one and go to the mark scheme. So it allows you to link from question paper to mark scheme. It's quite nice, especially if you want to spend some time doing some past years. Okay, so just noting it here for you. But in this case, since it's new, you would have to find it inside the Google Drive where you usually find your notes. It is here. Mine and yours will obviously look different. But under this folder, I've downloaded some past year questions also. Okay. Let's look at this one. This one is from number 22 last year, paper 4.3. There is a magnet on the end of a spring and a coil of wire connected to a sensitive center galvanometer. So this galvanometer can deflect to the left and deflect to the right, depending on where the direction of the current is. Okay, the magnet can move freely through the coil. What that means is the magnet won't suddenly get stuck up, or rather there is no significant amount of friction inside the magnet. Heavy rain. Okay. So the magnet is going to be able to move freely and down like so. I'm going to pull it downwards. Okay. So in this question, it says that the magnet is pulled downwards and then released. Describe and explain what happened to the needle of the sensitive galvanometer. So if we imagine that there is like magnetic field lines right here, so I draw a field. Not to South Pole. This one, oscillate up and down. This coil here, it will all cut the magnetic field line. Just keep cutting the magnetic field line. So because of this cutting magnetic field lines, there is induced EMF. You can write that down as part of Faraday's law. Okay, so I think I'll start by saying that as the magnet moves up and down, magnet moves in the coil. Coil cuts the magnetic field lines. Okay. So identify where the cutting is happening. Right, that's the first point. Because of this, and say there is electromotive force, short form EMF, induced in the coil. Okay, the word induce is compulsory because it's only applicable to this particular phenomena. Induce. So all you need is the magnetic field lines to be cut. But then there will be EMF induced in the coil. Okay, then you can then subsequently say current is induced in the coil. Okay, but they're asking you what happens to the needle, right? So as the magnet moves up and down, there is a change in flux in opposite direction, or rather, there is a opposition in opposite direction. So as the magnet oscillates, the induced current opposes the change causing it, which is the motion of the magnet. So this means when you pull the magnet down, the coil will pull the magnet up. When the magnet go up, the coil will push the magnet down. So because of this, the needle oscillates as the magnet moves. Okay, marks. Number 1. Coil cuts the magnetic field lines as the magnet moves. This one mark. Then there is EMF induced in the coil. 1 mark. I guess or you mention current induced in the coil also can. You have to mention the word induce and you have to tell me where the current is. It is in the coil. Okay, the next mark would be us saying that the induced current opposes the change causing it, which is the motion of the magnet. And finally, you talk about the needle. The needle oscillates as the magnet moves. This is the final one. Okay, so always think about using both the Faraday's law. So I think I'll list down the law here for you. There are 2 laws, 2 ideas to think about when you use electromagnetic induction. Number 1, is there a cut in magnetic flux? Then because of there is a cut, sometimes it can be a change, that it doesn't have to be a cut. So cut, or change. In magnetic flux. If there is a cut or change, then we have this induced EMF or current. Okay, and then the second law of electromagnetic induction is about direction. So this second law says that the direction induced current opposes change causing it. It's a bit like my parents caused me to be here, but I oppose them every teenage life. So this is Lenz's law, got name lah, but I don't think knowing the name is that important for IG. Then this is Faraday. Okay, so you can see the Lenz law is the last 2 marks, and then the Faraday law is the first 2 marks. So they can give you a scenario that maybe we haven't discussed before, because there are many ways I can cut the field lines. But go through these 2 points in some detail, it should be okay. But anyway, now we are going to replace the magnet with a stronger magnet. State the effect of using a stronger magnet on what happens to the needle of the galvanometer. So in this case, I would say that the galvanometer will have a larger deflection because it's a stronger magnet, right? So the needle have a larger maximum deflection, because there is larger induced EMF. Okay, finally, this one, I haven't taught you yet, but I think you've learned this before, so I included it, or rather I never cut this part B out. This is about a transformer. Okay, so later on when we study alternating current, Unit 4 is quite long, so we study alternating current Unit 4. I'll talk about what alternating current is and how transformer is used. But the idea of transformer, for example, right now I'm charging my laptop using the power plug. And I always must connect to an adapter, right? You charge your phone, you connect to the adapter. Without the adapter, your phone will die because 240 volt from the 3-pin plug So let's say you want to charge your phone. You know, you have an adapter here, then you got a cable here, right? So inside here, this 3-pin plug, this is 240 volt. If I use 240 volt and charge my phone will be a piece of toast. So I cannot put 240 volt lah. Most of the time, the phone only charged with 5 volt. So how did 240 volt input become 5 volt output? We use this device called a transformer. But most of the time, people like to call it adapter voltage to the voltage. Okay, but don't worry, this one we use ratio one. So in a transformer, let's say I draw the symbol of a transformer. Transformer actually consists of 2 coils. One coil here, then 2 lines here to separate the coil, and the other coil. Okay, so here I have input voltage. Let's say I call this V in. Okay, and then this number of turns is, let's say, N1 turns. So this is coil. Okay, we covered in your Kemahiran hidup, but never mind if you don't remember. So because of induction, meaning when I change the current in the first coil, I change the magnetic field in the first coil. And when the magnetic field in the first coil change, the magnetic field in the second coil change. We'll do an example of this. Okay. But in other words, later on, there will be an output voltage. So if I want to complete the circuit, this input voltage means here I connect an alternating current. Okay. This is alternating current. Okay, and then the output, I probably just connect this to a voltmeter, any output device. This output voltage will be V out, and then this is, let's say, N2. So it says here the step-up transformer is used to step up output voltage from a power station of 2500 volt to 400,000 volt for transmission along the power lines. Okay, so this means, right, my input voltage is 25,000 volt. And my output needs to be stepped up to 400,000 volt. Okay. The number of turns of the secondary coil is 3600. N2 is 3600. Primary, then only secondary. So the input is connected to the primary, the output is connected to the secondary. You go primary school, they only you go secondary school, right? Not reverse, right? So they're asking you to find the number of turns of your primary. So ratio is your best friend, right? So this means the ratio of input to output voltage will be the same as the ratio of the number of turns in the input coil, the primary coil, the first coil, to the number of turns of the secondary coil. And so we know our input voltage is 250,000. Did I just give you an extra zero? So 25,000. That's why I prefer to use prefix. Never mind. The output is stepped up to 400,000. I'm going to just preemptively cut the zeros. Okay. You are looking for N1, and your N2 is 36000. Okay. Which means your N1 will be equal to 25 over 400 times 36000. This would give me 2300. So it's kind of like if 2500 volt can give me, is given by 2300 turns, then this much voltage, 400,000 voltage, can be given by 360. So it's mainly about ratio. Okay. I mean, you can try and see, 2500 divided by N1 also can. This is 2300. This will also be equal to 400,000 divided by this. Personally, I prefer to ratio the same physical quantity because I can check my units, just in case, but it's up to you. Okay, so we'll talk about this more a bit later. But I want to move on to another question in the next page. Okay, but in other words, this one is just ratio. The more turns you have, the more voltage you will have. Okay, which kind of makes sense. What the more turns you have, the more induced current, so more voltage. So in other words, N is proportional to C. Okay, moving on. I think there is a double coil. There we go, like this one. So let's look at this question. Okay, we're going to start with one coil first. Let's not get too excited. Okay, here you have a coil containing a battery, a variable resistor, and a solenoid. Okay, I think this is page 6. So right now what we have is basically the solenoid being able to set up the magnetic field, and the direction is also drawn for us straight. Okay. So state how the magnetic field patterns indicates the region where the magnetic field is stronger. So generally speaking, we know that the magnet will be the strongest when the lines are the closest. So you see here, when the lines are very close, this is where the field is stronger, here. And then when the lines are far apart, let's say here, the field is weaker. Okay. So this one is a recap of magnetic fields. In this case, I'll say when the field lines closer together, the field is stronger. Okay, part 2. State what happens to the magnetic field when the current is reversed. Then this means that the direction of the field lines will also be reversed. You flip the current, you will flip the direction of the field. Because you use your Fleming's right-hand grid one. Change the direction of the thumb. Change the direction of the magnetic field. Clockwise, counterclockwise. Okay, beautiful. But we're here because we want to look at 2 coils. Okay, so here there is a second solenoid connected to a very sensitive ammeter. It's kind of like this one is the primary coil N1, and this one is the secondary coil N2. See? Okay, anyway, the variable resistor is adjusted. So I'm going to adjust this one so that the resistance changes quickly. State and explain what is seen to happen to the circuit of the second solenoid. Okay, in this case, right, we are not like moving anything. Okay, I didn't move large coil, the solenoid, the first solenoid, I didn't move the second solenoid. What I'm doing is I am adjusting the variable resistor. But when I adjust the variable resistor, I adjust the current. So say something along the lines where when the resistance change, the current in the first solenoid changes. And because the current in the first solenoid changes, the magnetic field lines in both first and second, in both solenoids, change. Okay, so there's a magnetic field here, there's a magnetic field here. So if I change this magnetic field, because the coil is inside the magnetic field of the first coil, if I change the magnetic field of the first coil, I will also change the magnetic field in the second. Okay. So because the magnetic field line changes, we can say hence there is induced EMF in the second solenoid. I care about the second one because the ammeter is connected to the second solenoid, or they're asking me what happens to the second solenoid. So then current flows and the ammeter needle deflects. Because actually what I see is only this ammeter needle deflects. Cannot see anything else. The rest is just, oh well, I adjust the resistance, I adjust the current. So for example, first mark would be when the resistance change, the current changes 1 mark. At least you know this lah. Okay, so don't leave this kind of thing empty in the exam. Just write what you know. Okay, even if you can't explain all the way, it's 2 marks. Right. Second mark would be the magnetic field lines in the both solenoids, specifically the second solenoid changes 1 mark. And then the final mark is there is induced EMF in the second solenoid and the ammeter needle deflects. Okay. Part 2, the variable resistor is adjusted much more slowly than in part. Okay, so that means the change is less more. So adjust slowly. So explain the difference that is seen to happen in the circuit of the solenoid. So I can say that because it's adjusted slowly, so there's a slower rate of change of magnetic field. Because of this, there is a smaller induced EMF and current. So because of this, deflection of the ammeter needle is smaller, less deflection. So you mentioned slower rate of change. The word rate is important. Okay, if you don't want to use the word rate, what rate actually means is change per unit time. So there is less change per unit time for the magnetic field. Okay, so that means that maybe in 1 second, previously the magnetic field will change by 10. Now the magnetic field only changed by 2. Still change, 2 is a change, but not as much in a given time. Okay, so there's a smaller current, and because of this, the deflection of the ammeter needle is smaller. So this one coil and two coil setting also can cause induced EMF. Most of the time, if we move something, there's a cut in flux, then it's like super obvious. But actually, I don't really need to, I can think about in terms of cutting, or I can think about in terms of maybe I can change the field. I can change the field by changing the current. Okay, because when I increase the current, I make the field strong. Decrease the current, I make the field weaker. Okay, so this is, I think that's all for this question. We're gonna, let's see, then another one. Okay, a few more. Wait. So this one is basically just focused on why is there current, and also why is there, how does the amount of current change when I change certain things in my setup? Mainly focus on Faraday's. So now I'm gonna pause the recording because I want to show you a video of a similar question. I don't want to be copyright strike. Okay, so the recording that I'm about to show you will show you an example of how when I put a magnet, so this is a tiny magnet, inside a copper tube, I'll let the magnet drop. Then I put it inside a plastic tube and let it drop. Okay, so I think before I let you see the video, since we have learned so much about induction already, you know that this is a magnet, and let's say this is north pole and this is south pole. Actually, and it doesn't really matter where it's north and south. Okay, but let's say this is north and south pole. So your magnetic field lines will be like this, you know, and it's in all direction, right? Because it's a 3D magnet, right? It's a 3D drawing. So you got these magnetic field lines like that, curving out of the magnetic field. So when I put it inside the copper tube, so imagine, this is your magnet bar here, magnet little cylindrical magnet here. And then your field lines are here. As it fall down, confirm will cut the copper tube. So then got induced current. Okay, but before I answer the question, let me show you this in a demo video.
Why will it be slower again?
Sorry, what?
Why will it be slower again?
Well, I guess we can write it down, but the whole idea about why the magnet will travel slower is opposition. Or in other words, the energy of the magnet is converted from kinetic to electric. We'll write down the explanation, because I think it's required in the question. Okay, so here, there are two tubes, by the way. There's a plastic tube and there's a copper tube. So one is made out of plastic and the other one is made out of copper. Okay, and the magnetic field of the magnet is very strong. So initially, the magnet is at rest on top of the plastic tube. And then it is released to fall through the plastic tube without experiencing a resistive force. Of course, for plastic tube, there is no induced current, right? Because there is no conductor, not a conductor. So there is no Faraday's law here because there is no induced EMF. Okay, and it says here that the magnet takes 0.67 seconds to fall to the lower end of the plastic tube. The mass of the magnet is 0.012. Calculate the kinetic energy when it reaches the lower end of the plastic tube. Okay, so I guess I need to be able to find the speed. I'm going to draw the plastic tube here. This is your plastic tube. Okay, I draw it a bit bigger. And you have your magnet here. And your magnet will eventually reach to the bottom here in a given time of 0.67 seconds. Okay, I have the mass of the magnet and I'm asked to find the kinetic energy. So if you can recall the equation for kinetic energy, Ke is equal to half mv squared. I already have m. So all I need is the velocity v of the magnet. this point here, this U is 0. So we can use your kinematics equation. In fact, we need to use your kinematics equation. All right. So there are a few ways to do this. I can use the equation acceleration is change in velocity over time. So how much did my velocity change? From v minus 0. How long did it change? 0.67. Do I have the acceleration of free fall? Yes. This magnet is undergoing gravitational acceleration. So A is equal to G, or 10 meter per second. 10 is V over 0.67. So from here, you can find the velocity as 6.7 meter per second. Then if you want to find the kinetic energy, you will take half mv squared. This will be half 0.012. And the velocity is 6.7 squared. This will give you 0.27. Very nice. You know the equation of KE, you get 1 mark. You know how to find the final speed, you get 1 mark. You find the final speed, you get 1 mark. Find the kinetic energy. 4 marks. Okay. So the first reasoning I can give you to why it takes a longer time to drop when I replace the plastic tube, it's plastic, with the aluminium tube is because I got current induced, right? The electrical energy will come from this kinetic energy. So the object will actually slow down. We'll put a bookmark on that first. And we're going to now look at the explanation section. Okay. The magnet is then held on top of the copper tube and then released. As it falls through the tube, there is an electric current generated in the copper. Explain why there is current in the copper. So I think I'll explain this one first. Put a typo this time. Okay. The reason why there's a current in the copper is because as the magnet bar falls, the magnetic field lines of the magnet bar is cut by the copper tube. Since copper tube is a conductor, plastic tube also got cut field lines, but plastic tube is like, sorry bro, I got no electron to move for you, so there's no current, no free moving electron. But copper tube got. So since copper tube is a conductor, there is electromagnetic induction. Current is induced. Okay. The whole idea is when the magnet bar falls, the magnetic lines of the magnet bar is cut by the copper tube. You can assume the copper tube is a lot of copper coil very, very close to each other, then become a tube. Okay. So because of there is cutting, there is induced EMF and also induced current. So the magnet bar falls, the magnetic field lines is cut by the copper tube. This is 1 mark. The second mark is when you mention the copper tube is a conductor, there is electromagnetic induction, current is induced. 1 mark. Okay, next. The current in the copper produces a magnetic field on its own in the tube. The magnet falls much more slower in the copper tube than the plastic tube. Explain why the magnet falls more slowly in the copper tube. Okay. So let's say You think about what I told you just now, where the copper tube is basically a lot of copper wire very, very close to each other. If I have many, many copper wire close to each other, doesn't it sort of looks like tube? Okay, but regardless, it doesn't really matter. All you need to know that this is a conductor. Because it's a conductor. And all these are like little wires all connected to each other. Okay, so I draw a few only, I can't draw the whole thing. Okay, and let's say the magnet bar is falling inside. Okay, and consider the perspective of the coil on top. Let's say this is South Pole, this is North. The coil on top is like, hey, magnet, 你去哪里? Why you go away? Why are you falling down? Come back up. So it will tell the magnet, please come back up, meaning it will try to attract the magnet. We zoom in a bit so I can move the magnet out of the way because I need to draw. So let's say the magnet already fall to this position. So this down, the coil down here is like, hey, you come back lah. So this one becomes not full. Try to attract the magnet bar. Please come back, magnet bar. I miss you. So this one is induced not to oppose the falling magnet. So that means there's a force like attracting the magnet bar upwards. Okay, let's consider the coil underneath. And remember, I told you the copper tube is like 很多层 wire 放在一起，总之是 conductor electron will flow already one. Okay, so now this coil underneath is like, hello, excuse me, bro. I'm minding my own business. Why you come over here? Please go away. So this coil will make this side up here not whole in an effort to tell the falling magnet bar to go away. So this is opposition or opposition force trying to push it away. So this is not pole again, induce to oppose the approaching falling magnet. Wow, this magnet bar life quite difficult. Just minding its own business, but experience a force in the upward direction from the top part of the copper coil and a force in the upward direction from the bottom part of the copper coil. So you can see the magnet bar experience opposition. Okay. So I would say from Lenz law, you don't want to mention Lenz over there, right? But this is from Lenz law. I just bracket and write his name. This is from Lenz law. We say that there exists an upward opposing force on the magnet bar. Since current in the copper tube, produces a magnetic field that opposes the motion of the magnet bar. If you don't want to say opposes the motion of the magnet bar, then you can say opposes the change causing it, which is the magnet bar falling. So the first mark, you might only say that there is an upward opposing force on the magnet bar. So be 1 mark. And because there is current in the copper tube, This current in the copper tube produces a magnetic field that opposes the motion of the magnet. Yeah. So imagine there are many layers of copper. As the magnet bar is falling, there is always a cut in flux. The cut in flux will cause an magnetic field. The magnetic field causes an opposition. So let me, I guess if it helps, I will draw out the magnetic field for you. It's back to normal. All right, so this blue section will have to feel like this. Okay, there's a magnetic field here induced in the copper, just like this pink section, this red section will feel in this direction. Sorry, it's not is here. So it's like 上面的把它吸上去，下面的把它推上去。Slow. Right. Any questions? Are you okay? Say, I want to say, since the magnet bar is slower, there is a form of kinetic energy is converted to electric energy. That's why it is slower. Okay. So I think later I'll send a video of different demonstration of this scenario. But just think about it. 因为那个 magnet bar 要跌下去，它就有那个 induced current， 那个 induced current 不爽那个 magnet bar， 所以就会把那个 magnet bar 推上去。That is Lenz's law. The magnet bar going down causes the induced current. The induced current is like, go away, I don't want you. But gravity is still going to be stronger lah. So it just falls over. All right, so think about it. We will continue this next week. Take care. See you. Don't get sick.
Thank you. Thank you, teacher.
Bye. Thank you.